Today we are going to look at Banach's fixed point theorem. This is also known as the contraction mapping theorem. I'm going to refer to a paper by Keith Conrad from the University of Connecticut. You can look him up in Google. I'm an accountant and I work in financial modeling, and I often see functions such as this, where the rate of change in the function is another function both of time and of the brought forward balance of the function itself, where the rate of change here might, for example, be sales volumes per month, and t is of course time. Now this here has the form of a differential equation. So I'm interested in differential equations, and to study differential equations one can look at the subject of real analysis, and this subject is particularly heavy in theorems. So why look at Banach's theorem? Well, it has various practical applications, such as being used in Picard's theorem, which is used to prove the existence and uniqueness of solutions to ordinary differential equations. It is also used to solve partial differential equations, and has an application in developing the Google PageRank algorithm. So various practical and useful purposes. We'll look at some examples later on. We will use a 5-step process for solving Banach's theorem. Firstly, we will define what a fixed point is. Next, we will use the intermediate value theorem to show that every function which is continuous in a range AB has a fixed point in that closed range AB. Thirdly, we will define what a contraction is. Then we will get into Banach's theorem proper. In part A, we will show that there is a unique fixed point. This will be a proof by contradiction. In part B, we will show that one can iterate to the fixed point. In other words, by applying a recursive method, one converges on the fixed point. And lastly, we will have a look at an example. Firstly, let's define what is meant by a fixed point. So this is where the output f of x is the same as the input x. Remember that the domain and range are the same. In other words, f is mapping x into x. Secondly, we will show that every function which is continuous on a closed interval AB has a fixed point in that interval AB. And we can use the intermediate value theorem for this. If we have a look on this axis with a and b defining the domain, and we construct a function f which maps the domain into the same range. In other words, the range is also the interval AB, because f is mapping x into x. Then we can see that f of a is greater than or equal to a, and f of b is less than or equal to b. So we can build an inequality where f of b minus b is less than or equal to 0, which is less than or equal to f of a minus a. And every value in this inequality is spanned because f of x is continuous on the range. So therefore, there is an x in f in the interval where f of x minus x is equal to 0. In other words, f of x is equal to x. Step 3, let's define a contraction. So this is for a function f which maps x into itself. There is a number q between 0 and 1 such that the distance between f of x and f of x prime is less than or equal to q times the distance between x and x prime for all x and x prime in x. Step 4a, Banach's theorem proper. here for a function f which maps x into itself and which is a contraction so that the distance between f of x and f of x prime is less than or equal to c times the distance between x and x prime with c between 0 and 1, we need to show that the fixed point is unique. So let's imagine this is not the case and that there is an a and an a prime in the domain which are both fixed points. Then this would give that the distance between a and a prime is equal to the distance between f of a and f of a prime because of the definition of a fixed point. And this would be less than or equal to c times the distance between a and a prime because f is a contraction on x. So left hand side fixed point, right hand side because of the contraction specification. And this would apply dividing by the distance between a and a prime, that 1 is less than or equal to c, which we know is not the case because c is between 0 and 1, so this is false. Because it is false, the fixed point must be unique. So 4b is the recursive part of Banach's theorem, and it's a precursor to that. This means that the nth x term will be the output resulting from the function of the xn minus 1 term. So in a graph, you see that x0 gives rise to f of x0, and this in turn becomes the x1 term. So there's your recursion. Similarly, the f of x1 term becomes the x2 term, etc., etc. With the curve as it is, you can see it's a contraction, so subsequent interval distances are getting shorter and shorter. And as they shrink to 0, there will be a point in the domain and the range where they converge, and in fact they will converge to the fixed point. A final thing before moving on to 4b in detail, we'll define what a Cauchy sequence is. So for a sequence aj with j going from 1 to infinity and all the j's natural numbers, for any arbitrary epsilon greater than 0 and for j greater than I greater than a number n, then the distance between the aj and the ai term will be less than epsilon. So getting into 4b, recursive part of the theorem in overview. Firstly, we will show that the sequence of x intervals shrink, so subsequent intervals are shorter, and in fact they shrink geometrically, which implies they form a Cauchy sequence. To prove that the sequence is Cauchy, we'll use a triangle inequality, which is that the distance between any points x and y is less than or equal to the distance between x and an intermediary point z plus the distance between that intermediary point z and y. We will choose a large number n, which is a natural number, and show that for n and m both greater than n, then the distance between xm and xn terms will be less than epsilon, i.e. the sequence is Cauchy. Because it's Cauchy, this implies that the x's converge in the limit to a point A. We will show then that for the continuous function f of x converges in the limit to f of a, which is the same as our point A. So why do we think that our sequence of x intervals is a Cauchy sequence? Well, the distance between the xn plus 1 and xn term is equal to the distance between the f of xn term and the f of xn minus 1 term. And this is less than or equal to c times the distance between the xn and xn minus 1 terms. The left hand side here is true because this is a recursive function. The right hand side because f is a contraction on this domain. So this implies that the distance between the xn plus 1 and xn terms is less than or equal to c times the distance between the xn and xn minus 1 terms, which is less than or equal to c squared times the distance between the xn minus 1 and xn minus 2 terms, etc., until we get c to the power of n times the distance between the x1 and x0 terms. So let's make this an upper bound of the sequence. So this implies that the sequence shrinks in proportion to the nth power of something less than 1, i.e. geometrically, which implies it is Cauchy. So now we use the triangle inequality to show that the sequence of x intervals is Cauchy. We have that the distance between the xn and an xm term will be less than or equal to the distance between the sum of all its subintervals. So distance between xn, xn plus 1 term, plus the distance between the xn plus 1, xn plus 2 terms, etc., all the way up to the distance between the xm minus 1 and xm term. Because this is a contraction that's less than or equal to c to the power of n times distance between the x0, x1 term, plus the c to the n plus 1 times the distance between the x0 and x1 terms, plus etc., all the way up to c to the n plus m times the distance between the x0 and x1 term. We can simplify this by factoring out the distance between x0 and x1. We end up with all the sum of all the c to the power of n terms on the left hand side times the distance between x0 and x1. And we can simplify the left hand side bracket as c to the power of n divided by 1 minus c times, of course, distance between x0 and x1 terms. Now we can pick a large natural number, capital N, and we can set little m and little n greater than that n, so that c to the power of little n times the distance between x0 and x1 divided by 1 minus c is less than or equal to c to the power of capital N times the distance between x0 and x1 divided by 1 minus c. And that's because c is less than 1, remember, and little n is larger than capital N. And this is all less than epsilon for any epsilon, so the sequence is Cauchy. So we have shown that the sequence of the xn terms is a Cauchy sequence, and X as a metric space is complete because it contains the limit point of its Cauchy sequence. So we can set the limit point to number a, to which the xn points converge as n tends to infinity. Now we need to show that the function f, which is a contraction on this interval, on this metric space, is continuous, and that f has a fixed point at a value a. Now we know that f will be continuous if we set c equal to 0, because then the distance between any 2 points of the function f will be equal to 0, because f is a constant function, and this is obviously less than the distance between any 2 x points on the domain, so f is continuous. For c greater than 0, we can choose a number delta, which we set equal to epsilon over c for any epsilon greater than 0. And we can choose a high enough iteration of the x prime interval such that the distance between x and x prime will be less than delta at that iteration. Then this means that the distance between the f of x and f of x prime terms, or point, will be less than or equal to c times the distance between x and x prime, which is obviously less than c times delta, which is equal to epsilon. And this proves that f is continuous. Now, as the xn terms converge to a, then the f of xn terms will converge to f of a. We know that because f is recursive, f of a will also be the xn plus 1 term. And the limit as n tends to infinity for xn is equal to a, and the limit as n tends to infinity of f of xn will thus also equal to f of a. And this is because on the continuous range, sequences converge to a unique limit point. And this means that f of a equals a fixed point a. So let's move on to the example. What we're going to do is we're going to use the theorem in looking for a numeric solution for the square root of 3. Let's just remind ourselves of what Banach's theorem is. This is for any complete metric space xd, i.e. a metric space which contains the limit of all its Cauchy sequences, and for a function f which maps x into itself, and where f is a contraction, then Banach's theorem says f has a unique fixed point, and for any x naught, which is initial value in x, the sequence of iterates x naught, f of x naught, f of x naught converges to the fixed point. Okay, we've refreshed ourselves of Banach's theorem, so let's move on to the example. We're going to show how Newton's iterative method ties in with Banach's theorem. Newton's method is an iterative one where the nth term of x is equal to an n minus 1 term of x minus a quotient of functions where the denominator is a derivative of the function, so that's g over g prime. The first term in the iteration is some suitable x naught. In this example, we set g of x equal to x squared minus 3, and f of x is equal to the entire iterative function, so equal to x minus x squared minus 3 over 2x. And we can simplify this down to a half of x plus 3 over x. So we're going to substitute for our x0 term now. What we'll do is try a value of 1.5 as the first term. So f of x naught, substituting into f of x naught is 1.75 equals x1, because this is an iterative function, and the f of x1 is equal to 1.73214, etc., etc. And we can substitute that in again. So having found multiple iterates, we now need to decide whether the contraction mapping theorem is a good fit for the scenario. And that means we need to determine whether x is a complete metric space for the function f. We know that it has to be the open interval 0 to infinity, because at 0 f would not be defined, but this interval is not complete as it is. So we imagine that there is some number t which serves as a lower bound for x. We know that the square root of 3 is the minimum value of f of x, so that might serve as a lower bound. But what if there is a t less than the square root of 3, which also serves as a lower bound for the metric space x? Now, to get this lower bound for the metric space x, i.e. that number t, we know that f of x minus f of x prime is equal to a half x plus 3 over x minus a half x prime plus 3 over x prime. And we can simplify this equation, work it through, so this works out to be a half of x minus x prime plus 3x prime minus 3x over x prime, which is a half x minus x prime times 1 minus 3 over x prime. So for an x greater than or equal to t and an x prime greater than or equal to t, because that's a lower bound in the metric space, we then have 1 minus 3 over t squared is less than or equal to 1 minus 3 over x prime is less than 1. So this will give 1 minus 3 over x times x prime, or the absolute value of that less than 1, which it needs to be for contraction, when 1 minus 3 over t squared is greater than minus 1, i.e. when t is greater than the square root of 3 over 2. So square root of 3 over 2 could also be a lower bound for the metric space x. So we can write that as the closed interval, closed on the lower bound of 3 over 2 infinity. But in practical terms, we note that when x is less than 3 over 2, the square root of 3 over 2, but greater than 0, this also works, because substituting in such low x values will result in an f of x which is greater than the square root of 3 over 2. So f of x will be greater than or equal to the square root of 3, even when the x naught term is less than the square root of 3 but greater than 0. That is, the first iterative value x1 will be greater than or equal to the lower bound of square root of 3. So x is a complete metric space, and the contraction mapping theorem does conform to this example in this space. Finally, please note the following amendments and corrections which will improve the overall correctness of the video. Firstly, at around about 4 minutes and 45 seconds, to be entirely consistent, we should use a contraction constant of C instead of Q when defining the contraction. Just as a reminder of this definition, this is for a function f which maps x into x. There is a number c between 0 and 1, such that the distance between f of x and f of x prime is less than or equal to c times the distance between x and x prime for all x and x prime. Point B relates to the triangle inequality which we use to show that the sequence of x intervals is a Cauchy sequence. As a reminder, this inequality is that the distance separating the xn and xm points is less than or equal to the length of the xn plus 1 subinterval plus the xn plus 1 xn plus 2 subinterval length plus etc up to the distance separating xm minus 1 and xm. And this is less than or equal to c to the power of n times the distance between x0 and x1 plus c to the n plus 1 times the distance separating x0 and x1 plus etc all the way up to c to the power of m minus 1 times the distance between x0 and x1. Please note that this should be c to the power of m minus 1 and not c to the power of n plus m as we had in the video at around about 12 minutes and 10 seconds of the way through. Correction C refers to a point about 16 minutes and 30 seconds through the video. We had shown that the limit as n tends to infinity of xn equals a, and f is continuous, so f of xn tends to f of a as xn tends to a. Also, f of xn equals xn plus 1 because the function is recursive. So f of xn tends to a as n tends to infinity. Please note the correction is that this becomes f of xn and not f of a as per the video, and that completes that correction. Correction D refers to a point 24 minutes and 53 seconds through the video and relates to the example. The correction is that the video should say f of 0 is not defined and not that f of x is not defined. Just again, f of x not defined is wrong, except at 0. Finally, I would just like to say thank you to Keith Conrad for providing some detailed review comments which have been helpful in putting these corrections together and ensuring the integrity of this video.